Okay, so like I mentioned, we're gonna start in, do 2 practice problems with the ICE tables, just to make sure that we're feeling comfortable with them. And then we're gonna talk about Le Chatelier's principle, which is relatively straightforward. I feel like maybe I rushed too much at the end of last class and they were confused, but it's relatively straightforward. So let's start with this one and have you guys work through this. Remember that K is small, so you're gonna wanna make that approximation that we talked about in last class. The other thing is I'm gonna just give you these in atmospheres. I'm not gonna have you converting them on a test because I don't want you to get it wrong because you used torr and not atmospheres. So use these atmosphere values in the problem. Okay? And we'll just go over that in just a couple minutes. Be right back. So in case you forgot, the thing I mentioned about ignoring the minus x or plus x, that's when the k is 10 to the negative fourth or smaller. So it's 10 to the negative fourth here. So what we're gonna do is make that approximation that we can ignore these amounts. Because what we're saying is that those are gonna be small enough that it's not gonna change this number. It's like, maybe it was 0.993 before, and maybe it becomes like 0.992, and we're like, that's not a big enough difference to matter, okay? So we're gonna get rid of those, and that'll simplify our math a ton. So I forgot to set a timer when we started this, so I don't know if I did that too fast or not. But the question is asking for determine the equilibrium concentration of BRCL. So once you get X, now you've got to plug that in because it says equilibrium concentration. Okay, so that's 2X. So I'm going to multiply X by 2. Okay? Now, if this had been 1.11 times 10 to the negative third, then you would want to leave that minus X in there, and you would end up having to solve the quadratic equation. Yes, on the homework. I'm not going to do that on the test, though. So you're going to see problems like this on the exam, not ones where you have to solve the quadratic. The key point is like, if you forget to make the approximation and you're like, oh, why do I have not, she said we weren't going to have to solve that. It's probably because you forgot to do that approximation, okay? To ignore those minus x's, or it could even be a plus x in the equilibrium column. We're not talking about the change here. We're talking about when you get to the equilibrium amounts. If it's plus or minus x, that's when you get to ignore it, not multiplying by x, because then you get 0 and the whole thing wouldn't make sense. Okay, so on the next one, you need to read carefully, and it's not the same format as the others. It's not like you're starting with all the initial amounts and finding out the equilibrium and solving for x. It's a little bit different. So you want to follow all the same steps, though, of set up the ice table, decide which direction the reaction goes, define the change, define the equilibrium. You go through all the same steps. It's just that once you go through all those steps, hopefully you're going to be able to see how to get to the answer, okay? So it's a little bit less familiar. So go ahead and take a few minutes to get started on that, and then I will start working it up here as well. And similar to the other one, this one's in moles and tells you the liter. So I'm just going to rewrite that for you. This is 1.3 molar and 0.6 molar. Okay, so just before you do any solving, let's take a look at this one. So you still want to put any of the information that's in words, you want to put that into your ICE table. So find the amount of NO that must be added to 1.3 molar of SO2. Okay, they're saying we're going to mix the two reactants. One of them, the SO2 is 1.3 molar, and one of them, the NO2, we don't know how much we should put in. That's what the question wants. So I'm going to label that as question mark because that's what the question is asking us. Like, is it also 1.3 molar, or is it 10 molar, or is it 2 molar? We don't know. But there's some amount of the two reactants we're going to mix together. And then it says, in order to form 0.6 molar of SO3 at equilibrium. So I'm going to come to my SO3 and put 0.6 molar. All right? These are the only two pieces of information you know, and this is what you're looking for. Okay? So initially, that's all I have in my ICE table. Then I say, okay, I know I'm not starting with any of this because they didn't say anything about that. And that tells me the reaction has to proceed towards products because there's none of the products to start with. So that allows me to define my change, minus x and plus x, all the coefficients are 1 here. And then I can define my equilibriums in terms of x. Okay, so when I look at this, initially I'm like, I've got all these x's, I've got this question mark, like what's going on? I can't have two unknowns here, so there must be some more information. Well, when I filled in these equilibrium amounts, remember it's this and that make this. So 1.3 minus x, 1.3 minus x, question mark minus x, question mark minus x, 0 plus x. Oh, it's telling me that's 0.6. It's telling me, once I fill out the ICE table, I now know x equals 0.6, right? Because 0 plus x was equal to 0.6. So now, knowing that x is 0.6, I can go fill in everything else and eliminate that as a variable. So I can say, okay, NO is 0.6, SO2 is 1.3 minus 0.6 or 0.7, and then this one is still question mark minus 0.6. Now I only have one variable, and I can go ahead and plug this into the K expression and figure out what is that amount of NO2 that I have to mix with 1.3 molar SO2 to get me that 0.6 molar SO3. Okay, so go ahead and set up your K expression and plug in those values and then solve for your question mark. If I was a math teacher, I would have labeled that as Y, but I wanted to be really clear that that is answering our question. The question is asking us about the amount of NO2 initially. Okay, so a few more minutes and I'll let you guys solve that.
Where'd you get that 0.7?
1.3 minus 0.6.
Yeah, because I was wondering, because SO3 is 0.6, right? And then SO2 is 1.3, right?
Yes. Yeah.
Yeah,
So first I had to find out that X was 0.6, and then this says it's 1.3 minus X, so 1.3 minus.
Oh, so you get
0.6.
X is 0.6.
Yeah, that's like the key thing that allows you to solve it, is when you realize that it starts with 0, turns into 0.6, now I know what X is. So that's how much reacted off of the two reactants.
Is that because NO is 0, so it doesn't
Yep.
change?
Yep.
So it's like 0.6 plus 0 is 0.6.
Yeah, exactly. Okay, so when you do the math, you get that question mark. It feels silly doing a math problem with a question mark, but you get 0.76. Okay, what does that mean? It means if I react 1.3 SO2 with 0.76 NO, and then I let them get to their balance point, I'm going to be left with 0.6 of both products, SO3 and NO, and then these equilibrium amounts of the reactants, okay? But they're asking you, like, when you mix a different amount of reactant, like if I were to mix 1 molar, I would get a different value for the products because that offsets my K expression, right? So I have to know precisely how much to put in if I'm looking for a certain amount of product. So just be aware that there are some questions like this that are maybe not quite as like formulaic as some of the other ICE tables. A lot of the ICE tables are just like, here's your starting amount, change, equilibrium, solve for X, whatever. This one's a little bit more, takes a little bit different type of thought pattern to recognize that you actually know what the change is in this case because you're given an equilibrium amount. I think we did one more like this at the very beginning of when we started doing ICE tables, but.
Can you use a variable for a question like this, or does it need to be a question mark?
No, I mean just use like Y or something.
Okay.
Yeah, it'll look nicer. It feels weird using a question mark, so. Just don't use X or else you'll get confused.
Yeah. Use like Z or Y. Or
Yeah.
something, or
Yep.
T or
Whatever. For that matter, you could just plug in concentration of NO2 initial or something.
Yeah.
Okay, so the rest of today, we're going to talk about the last section of Chapter 9, which is a concept section, and it's called Le Chatelier's Principle. And if you remember from the reading, I know that was like a week ago or something, but the idea of Le Chatelier's Principle is with equilibrium, we have some balance point, right? That the reaction is naturally going to tend to. So if we have the reaction at its balance point, and then we do something to offset that, it's going to go back to its balance point. The way that it's phrased in Le Chatelier's Principle is that, let's see, do I have it in words here? No, I'll just write it. Yeah, okay. So if we put a stress on a system, and we're assuming this system is already at equilibrium, the reaction is going to shift. So reaction will shift, and by shift, I mean it will either react towards products or it will react towards the reactants to relieve that stress. I need to come up with an analogy for this. I don't have a good one off the top of my head. Maybe I'll get one as we're working through it. No. Can't. Okay. So, yeah. So just be clear when I say the reaction shifts, because it's going to keep asking that. Which way will the reaction shift? It means, are the reactants going to turn into products, or are the products going to go back and turn into reactants? Okay. Like there's going to be a reaction occurring to rebalance the equation. Okay. So I'm actually going to start with the picture. So skip this page and let's start here. So one of the most common things that we do to create a stress is to add in or remove, but in this case it's adding in either some more of the reactant or some more of the product. Okay? So in this example, you've got this situation, this reaction in equilibrium. So N2O4 turning into balanced out with 2NO2. So you can see the system at equilibrium. You've got some NO2 in here and then some N2O4. So it's at equilibrium, and then we dump in some extra NO2. So if you think about it like the balance point, it's like we're here and this is where we want to be, but now we just put in some of the product. Like we just dumped it into the system. So that's the stress, dumping some stuff in the NO2 into the system. So the reaction has to relieve the stress. The way it does that is by using up that NO2 and making more N2O4. So it shifts from NO2 to N2O4 because in that process, those NO2s are reacting with each other, right? And turning into N2O4, and that gets rid of some of that NO2 that you put in there. It's like I pushed this amount up. When we say a stress, we mean like externally we did something to the system. How does it respond? So I push some of that up. The only way to get rid of that is by the reaction reacting towards reactants, and that'll help bring down some of the NO2. In the process, you're also going to make some N2O4, right? Like you can't help that, but that's okay because that's rebalancing that ratio. If you want to think about it mathematically, the K in this case is NO squared over N2O4, right? If I increase the top number, the reaction shifts this way. That helps to increase the bottom number and drop this one back down a little bit, because the whole point is it's trying to keep this ratio the same, okay? So if I make this number too big, the way to balance that out is by increasing the bottom number, okay? It shifts towards this direction. All right, so let's look at this example above. Let's just do one or two of them together, and then I'll have you guys predict. So it's this very generic chemical equation. It doesn't have any, meaning. I just made it up. And let's do decreasing C. We'll do that one together. And increasing, B. Okay? All right, so in the picture we had before, I increased the product. It used up some of that product and shifted it towards reactants to balance it out. In this case, the stress, so I'll write the stress in red, is increasing B. So I dump some B into this container that's already at equilibrium. That's the stress. And it's like, I have too much B. I've got to get rid of it. How do I get rid of it? I shift it towards the products. I react some of that B with A, because that's how a chemical reaction works. I can't get rid of some of that B without also reacting it with A. And then the reaction shifts towards the products. Be aware that in that shift, usually the question is just going to ask that. Which way does the reaction shift? It could also ask you, what happens to the concentration of C as a result? Well, it would increase, right? If the reaction is shifting towards products, you're making some of the products. That C is going to increase. Okay, what about decreasing C? I'm going to erase this. So the stress now is I remove some of the C. This is actually a really common way to get more product out of a chemical reaction. So if you have a balance point that, let's say the balance point is reactant favored, but the whole point of you doing, this chemical reaction is that you want C. So maybe you're synthesizing a drug, and you need to put that drug into a pill and sell it, right? You want to get as much C as possible. Well, if it's reactant favored, how are you going to get enough product out of there? So what they do is they let it go to equilibrium, and then they take some of the product out, okay? So that's what this one is. We're removing some of C. So you've offset that equilibrium by removing some of the product. So the reactant goes and makes more product to try to rebalance it. So that's the shift. It moves towards the product to rebalance it. And then they just keep doing that over and over. It gets to equilibrium again, and they say, okay, let's take some more of the product out. Then the reaction shifts to product again until you basically hit the end where you can't really make a whole lot more. But it's a way to, we say it's driving the reaction to products. Okay, so take a minute and predict these other ones. Just the direction that the reaction will shift in response to each of these. Okay, so I'll put them up there and you can check your answers. Okay, so briefly to summarize it, these two are reactants, right? If I increase the reactants, they're going to get pushed towards products. So they shift towards the products to get rid of those extra reactant. If I decrease the reactant, A, B, the reaction's going to shift back to replace them. Let's see, if I increase the product, it's going to shift away from that to use some of it up. If I decrease the product, it's going to shift towards it to make some. So whatever the stress is, the reaction shifts in order to alleviate that, to undo it. Think of alleviating it as undoing that stress. Okay, so there's, other than adding stuff in, there's two other ways that we're going to talk about how we stress a reaction. The first is, well, the first one that's in the notes is changes in pressure. Could be typically as a result of a change in volume. But I want to talk about changes in temperature first. So I'm going to scroll down a few slides to this one. Okay, so this reaction is endothermic. And they would have to tell you either that it's endothermic or that the delta H is positive, right? Because that's another way of saying endothermic. So in an endothermic reaction, heat is required in order for the reaction to proceed. In an exothermic reaction, it's produced as part of the reaction, but in endothermic, it's required. What that means is that in an endothermic reaction, we can think of heat as being one of the reactants. Because if it's required just like, matter, the N2O4 is required. So that's why they've rewritten this equation not just as N2O4, but N2O4 plus heat. They're adding it in on the reactant side. We'll look at another one in a second where it's exothermic, where it's on the product side. Okay? Okay, so we're assuming we have this reaction at equilibrium. And then in the two pictures, in the one on the left, we decrease the temperature. Now, I don't know if you can see that. It's, it says -75. Oh, they must have added like liquid nitrogen is probably what that is. And then on the right, it's 26, okay? So on this one, we decreased the temperature. On this one, we increased the temperature, okay? So those are our stressors. I should have written them in red. So what happens when we decrease the temperature? Well, temperature, heat, those are pretty much the same thing. We're going to decrease the temperature, okay? So we're dropping the heat. So if we're treating it just like a reactant, the reaction will shift to replace some of that heat. So it shifts towards the reactants. So as we decrease the temperature, the reaction shifts towards the reactants. And in this particular example, the N2O4 gas is colorless and the NO2 gas is brown. So when you have this system in equilibrium and you drop the temperature, now I don't know exactly what color it is at equilibrium. It's probably some pale brown and it just gets darker or lighter depending on the temperature. But if you decrease the temperature, it shifts towards the reactants, and so you get more of the colorless gas. If you increase the temperature, so I'm going to change the direction of our arrow. So increasing the temperature, increasing the heat, it drives the reaction towards the products now. It's trying to relieve that pressure by getting rid of some of the heat. Okay? In the process, it makes NO2, and that's why the thing turns brown. So when you're talking about heat, they have to tell you whether it's exo or endothermic, and then you treat it as a product if it's exothermic or a reactant if it's endothermic. Okay, so let's try that one on the slide above. No, not the slide above. 2 above, this one. 2x plus 4y, okay? So take a minute, read through these questions, and predict which direction the reaction will shift in both of these.
Back on the increasing A, B, and C thing, when you're increasing A and B, when you're shifting it right, like
This one?
increasing it above equilibrium or decreasing?
Yeah, so if it says, so give me, which one you want to talk about? Increasing A?
Like A versus C, for example.
Right, so if you're increasing A, you're putting too much reactant, so it needs to get rid of some of the reactant. So it goes towards products, uses it up, reacts it, makes products instead. If you're increasing the product, now you've got too much of the product, so it goes the other way to get rid of some of it. So if you want to think about it mathematically, it's like, are you increasing the denominator or are you increasing the numerator?
So A is like too much reactant, and C is too much product on
Right.
the left shift.
Yes. So it shifts to get rid of some of that, whichever one it is. Okay, so if you didn't make that connection yet, it's negative enthalpy, so that means heat is a product in this one. Okay, so in the first one, you're increasing the temperature, you're increasing the thing on the product side, you gotta shift away from it to get rid of some of that. So that goes to reactants. And then the opposite, if you remove the heat. You remove some heat, it's gotta make more of it. It shifts towards the products. Okay, so the last stressor we'll talk about is changes in volume, which really is a change in pressure, okay? So here's our picture for that one. So if you remember, and if you don't remember, just memorize this, because I know there was a class that didn't do gases, so putting this out there. So if you have a decrease in volume, that will, they're inversely related. It will increase your pressure. And same thing is true opposite. If you increase the volume, that will decrease the pressure. So the stress here that we're talking about is the change in pressure that occurs due to the change in volume. Now, the other thing to remember is that pressure is affected by the number of moles of gas. So I'm going to say pressure is proportional, remember that's what the little fishy is, to N, which is the number of moles of gas. Okay? So if I increase the pressure, that's what's happening on this side of the reaction. We dropped the volume, so the pressure is higher now because the molecules are hitting the sides of the container more. The reaction has to shift to relieve some of that pressure. So the way it does that is it goes to whichever side has fewer moles of gas. So in this case, there's 1 mole of nitrogen and 3 moles of H2, so 4 total. And over here, there's 2. So the reaction will shift towards the 2 in order to bring that pressure back down. So the stress was you increase the pressure, the reaction responds by making more product, decreasing the reactant, making more product, shifting to the product side in order to relieve some of that pressure, because fewer moles of gas will result in less pressure. And then the reverse would be true. If you increase the volume, that decreases the pressure. So the reaction will shift back to the side with more moles of gas to kind of bring that pressure back up to where it was before. So for our last practice, let's look at this one. Sorry, I'm kind of out of order. So it says which of the following will cause a decrease in the concentration of Z. Just start by telling me the shift. Which way does each of these cause, what shift does each of these cause? And then we will talk about how that affects Z. So I'll tell you right now, because we haven't talked about it yet, catalysts don't do anything. They speed up a reaction, so it'll get to equilibrium faster, but it doesn't change the balance point at all. So just look at those other 3 and predict which way it'll shift. Because it's positive here, so that's endothermic. So endothermic is a reactant required. Yeah, good question. So increasing the size of the container, that drops the pressure. So you do have to memorize that basically if you don't remember it from when we did gases. If the volume goes up, pressure will go down, and vice versa. So if you drop the pressure, it's going to shift to wherever there's more gas to bring that pressure back up. So that's the reactant side. Increasing the concentration of X, it's a reactant, it'll shift to get rid of that to the product side. And then because it's endothermic, heat's a reactant. So if I increase the temperature, it's just like increasing a reactant. It'll shift to the product side to get rid of some of that. So which of these actually causes a decrease in Z? The first one's the only one that would cause a decrease in Z because it's shifting to the reactants. It's going to use up some of Z in the process. Okay, so lots of these, just concept ones on the homework to make sure you're comfortable. Concentration changes, pressure changes, and temperature. And then homework is due Sunday night, and then we will do question time on Monday. So I'll always bring some in, but ideally if you guys like even just questions from the homework, like topics that you want to do more on. Any questions for me, Colton?
I actually had one about a question